Let's talk about galaxies. So this image is the Hubble Ultra Deep Field. It's a portion of the sky that's 1/10 the diameter of the moon. So it's a really tiny fraction of the night sky. It required 800 exposures taken over 400 Hubble orbits, which is like 11.3 days. And it was the deepest image of the universe ever taken at the time. Now, Hubble's predecessor, James Webb Space Telescope, has its own version. Um, and maybe there's more than that too. The image contains 10,000 galaxies. Um, and Many galaxies in this image were at least candidates to be the most distant astronomical objects discovered. This image is looking back 13 billion years, and every speck of light you see in the image is a galaxy. So this is Hubble's tuning fork, which is just showing different types of galaxies and kind of like their structure, but we'll get into that with pretty pictures. So here we have the galaxy types. We have spiral, looks like this, barred spiral, elliptical, and irregular. And we're going to talk about each of these. So spiral galaxies, that's what the Milky Way and Andromeda are. They're a flattened disk with a central bulge and an extended halo of old stars. The halo is a specific term when talking about galaxies, and it's kind of extends beyond what you see as the parts of the galaxy, but that's still like gravitationally bound to the overall thing. Um, and the stellar population, so in the bulge and halo, there's red old stars and globular clusters, which are really dense groups of stars that are gravitationally bound to each other. The disk itself is rich in gas and dust and forming new stars. And most of the light is coming from those bright, massive young stars within the disk. So that's why that's what we primarily see. And you don't have to see the spiral arms in order to classify a galaxy as a spiral galaxy. A presence of a disk with gas and dust and young stars is actually enough to qualify as a spiral galaxy. But because galaxies can be oriented anyway toward our line of sight, like it makes sense that you don't have to see spiral arms to call it a spiral galaxy, because these three here, for example, are all like giving us a side view. And from the side view, you can't necessarily tell if there are spiral arms, but you can definitely see the dust and gas and young stars. Especially here, you can see the blue, bright young stars. There's a barred spiral galaxies. They have an elongated bar of stellar and interstellar matter. Interstellar matter just means the stuff in between stars that pass through the center and extend beyond the bulge into the disk. And the Milky Way actually does have an elongated bulge, but we aren't sure about the full extent of it, for one thing, because we can't see it. We're in the galaxy. We can't see the outside. But here's three examples of barred spiral galaxies. So they have the spiral arms, but then they also have this like elongated area in the middle. Then there's elliptical galaxies. The structure, there's no spiral arms and usually no obvious disk. The only real obvious thing is an overall dense central nucleus of it. Otherwise, there's little internal structure. It just kind of looks like a hazy glow. There's little to no cool gas or dust. X-ray observations show large amounts of very hot, several million Kelvin, which Kelvin is like 372 sorry, 0 Kelvin is 372 Celsius. I'm messing it up, but don't worry, it's like Celsius. Anyway, it's really hot. Interstellar gas is distributed throughout the interior, and often extends beyond what we can see, like the visible portion of the galaxies. There's no evidence of young stars or ongoing star formation that really requires that gas and dust and interstellar material. So it's mainly old, red, low mass stars. And really, what we're seeing is mainly just stars. And there's irregular galaxies. The visual appearance of these does not allow them to be classified as spirals or ellipticals. But they are rich in interstellar matter and often have young stars because they have all that dust and gas that stars need to form. They lack regular structure. Often they're smaller than spirals and larger than what are called dwarf ellipticals. They contain 10 to the 8 to 10 to the 10 stars. And the smallest versions are called dwarf irregulars. And often they get their shape and structure potentially from collisions with other galaxies. So now I want to shift. We're going to talk about our galaxy, but first I need to talk about a measurement of distance. Light years are a measurement of distance. It's the distance it would take light to travel in 1 year, traveling at the speed of light, which is almost 700 million miles per hour. The sun is 8 light minutes from the Earth, so it takes light 8 minutes to get from the sun to the Earth. And the moon is 1.3 light seconds away. So let's look here. The Earth's diameter is 0.0425 light seconds. So light travels across the Earth's diameter real quick. The solar system's diameter, that means like from one side of the biggest orbit to the other side of the biggest orbit, is 3 light years. So it takes light 3 years to get from one end of the solar system to the other. But the diameter of the galaxy is 100,000 light years. So way huge in comparison to our solar system or our planet. And then after that, the distance to the nearest galaxy is 2.5 million light years. And the size of the observable universe, so the stuff we can see, is 14 billion light years because the universe is 14 billion years old. This is our galaxy seen from Earth. All this here, and hopefully from the bit about galaxy classifications, you see all of this gas and dust, and that might lead you to think that maybe we are in a spiral galaxy. Here is what the features of our galaxy kind of look like. We have a galactic disk, which the Earth sits in the disk, and then we have the bulge and center. So the galactic disk is a circular flattened disk containing most of the galaxy's luminous or bright stars and interstellar matter. There's the bulge, which is roughly spherical, and it's at the center of the galactic disk. The galactic center is within the bulge, and it's the dense central region of the galaxy, and that's also where the supermassive black hole at the center of the galaxy is. And then the galactic halo is roughly spherical ball of faint stars surrounding the disk. So it's not listed in this image, but it would be beyond what is seen here. There's the halo. This is another view of kind of like where we are in the galaxy. So the sun is out in one of the outer spiral arms, but we can look toward the galactic center. So here, this image or diagram, it's not really an image, shows the galactic halo. So it's this like barely visible in this depiction, and has virtually no gas or dust, so there's not new stars forming there. And there's globular clusters, which I said are star clusters with like a ton of stars in them, and all those stars usually formed together like a long time ago. The disk and bulge has lots of interstellar matter. The bulge and halo stars are redder than disk stars. So bulge and then the halo, those are going to have redder stars. And then the stars in the disk are going to be bluer because those younger stars tend to be bluer in color and older stars often are red in color. Um, and because all of the gas and dust is within the disk, that's why we see young bright stars in that area because all the stuff needed to form stars is there. And I already said that the gas-rich disk is the site of ongoing star formation. Um, and that the halo, again, because there's no gas and dust, no new stars are forming. So that's a little bit about galaxies and our own galaxy. Thank you.